Chapter 2 is on what we call arithmetic sequences. So an arithmetic sequence is the simplest sequence to some degree that we can make. We've seen this before. I'll just take this example. 1, 4, 7, 10, 13. We've seen that in the previous one. And it's simple in the sense that I'm just adding something. So plus is always the simplest of the operations. And I'm adding the same thing every time. So I have that consistency as well, making it very straightforward. So I'm just gonna write this sort of definition out, but it's this kind of sequence we are describing. So an arithmetic sequence, I need to know two things to make this sequence. I need to know what is the first term. In this case, it's a 1. And I need to know what do I add every time. We'll call that the difference. 3 in this case. But this is just an example, right? It doesn't have to be a 1 and a 3. In general, I can replace this 1 with maybe an A, or A1, if you will. And in general, I don't have to have a difference of 3. I'll call it D for difference. So then I get a sequence of the form. It has a certain look to it, a certain form. I'm going to start with my first term that I'll call A, maybe a 1, maybe something else. Then I'm going to add that difference. And without knowing exactly what they are, I can't really simplify it. So it's the first term plus the difference, A plus D. Then when I add another D, I really have 2 Ds from the start. When I add another D, I really have 3 Ds. So I keep adding another D to go from one to the next. In specific examples, I would know what the values of A and D are, but in general, I don't know. So we're trying to make the sequence as simple as possible while still having some variety. So the recursive formula we have seen before. It's going to be specific to our example. We've seen that one as well. It's a translation of what we've described in words. To get a term in the position, I need to take the previous one and add 3. But in general, without knowing exactly what the numbers are, I have to say I take the previous one and add this difference, whatever that may be. So it's sometimes helpful, very often, to look at a specific example, but the definition really phrases the concept in general terms, not specific numbers. But you can use a specific example or the general A and D however you want. The explicit formula, however, let me just check before we do that. How do we feel so far? Again, we're trying to make things as simple as possible by getting rid of as much variation as we can, because that's where the complications come in. So we have 2 kinds of formulas, recursive, okay, fine. We've seen this before, and explicit. Now let's just, for our example, do some work on the side that might help me. I need to scribble some stuff to figure out why the explicit formula looks the way it does. And once I've figured it out, I can maybe just remember the explicit formula. But that first one, for me, needs some explaining. So let's look at the example up here. And of course, I have positions for these terms, just like always. So an explicit formula, I know, uses only the position value. So I need to find a link between the position and the term in that position. For me, a table is very nice. I don't know why, it just works for me. To show the pattern a little bit, as obvious as it can be. So I want to find a link between the position and the term in that position. And I have positions 1, 2, 3, 4, 5, and of course it just keeps going. So position, what was the sequence? 1, 4, 7, 10, 13, and so on. So often to find this link, I leave the first one for now and go to the second one. I know that takes the previous term, and I add 3. Then the 7 is taking the 4 and adding 3. That's how I get 7. But the 4 itself comes from 1 plus 3. And then I add another 3. So I'm trying to pull these numbers apart to see where do they really come from. And can I sort of see a pattern in their calculation? 10 is the previous one according to the recursive formula. It's the previous 7 plus 3. That's how I make the sequence. But 7 itself is 1 plus 3 plus 3. And then I add another 3. 13 is the previous 10 plus 3. But 10 itself is 1 plus 3 plus 3 plus 3. And then I add another 3. So I definitely get increasing numbers. So now let's see. The only thing that's changing here is the number of 3's that I'm adding. When I get to 7, it's 1 plus 2 times 3. The 10 is then really 1 plus 3 times 3. And the 13 is 1 plus 4 times 3. And I can now go back and say, well, the 4 is actually 1 plus 1 times 3. And the first term is technically 1 plus no 3. So it all fits that calculation pattern. Now, in trying to find an explicit formula, all I need to do is find a link between the position and the calculation in that position. A lot of those things are the same. The 1's always there, the last 3 is always there, but there's something that changes. What is the link between the position and the changing thing? Can anyone see a connection between the position and the part that's changing in the calculation?
The position minus 1?
This changing part is always the position minus 1. If I'm in position 5, it's a 4. If I'm in position 4, it's a 3. Position 3 is a 2. So if I'm in position n, what is this going to look like?
N minus 1?
It's going to be the 1 is always there, plus a certain number of 3's, n minus 1 times 3. Now that's specific to our example, but we can certainly write that up here. So this was what I needed, perhaps, to understand where this comes from. So we'll do example. N is 1 plus n minus 1 times 3. And in general, I'm not going to know what the first term is, but there's a reason this is 1 every time. It's the first term. Not that one. This one. So in general, it's not going to be a 1, but whatever the first starting number is, that's the one that's going to always be there. And then n minus 1 times not a 3 necessarily, but the difference. Let me just have brackets. There we go. So that now explains and clearly defines all the different aspects of this arithmetic sequence. You can have an example, you can have specific formulas, you can have general formulas without knowing exactly what the first term and the difference is. But the recursive formula needs a little bit more, right? I didn't actually say that. The recursive formula always needs a starting number. In the example, it's a 1. In general, we'll just call it A. Sorry, I forgot that. Those are ugly, ugly curly brackets. There. Recursive formula has a starting point and then telling me what to do. The benefit of the explicit formula is it doesn't need a starting point. It just needs to know the position. And that's the only thing that features in the calculation. So, quiz number 1, page 2, is this that you're seeing on the screen. Explain what an arithmetic sequence is and give both types of formulas. You can use the A and the D. You can use specific examples. Doesn't matter to me because they look the same. Any questions on what you see on the screen there? Yeah.
So recursive has a starting point.
Yeah, because it's only telling me how to go from one to the next.
Okay.
So I need to know where to start to get things rolling.
And explicit, can you just describe that?
Explicit only needs to know what position do you want to calculate, and then it's using the position value in the calculation. No other previous terms, like this one. All the numbers are there. The only thing that I use to calculate the term in that position is the position value.
And those are 2 examples of arithmetic sequences. Or is that a
It's
completely different?
the 2 formulas are just different ways to describe the same thing.
Okay.
Yeah. And they have pros and cons to each of them. The recursive formula is a more direct translation of the pattern that I see, which is add 3 every time. It's specifically just rephrasing. Where's my cursor? Oh, there it is. It's specifically rephrasing the add 3 every time. But it turns out that in calculations it's not as easy to work with. The explicit formula is a little bit cleaner in that it doesn't rely on me building it up sequentially. I could jump to position 100 and know what that number is because that's all I need, the position. So it's a little freer, but it's not as easy to maybe read this as the recursive formula is. So they're both useful, pros and cons to each one. So when you state or when you talk about an arithmetic sequence, you have to mention the first term, you have to mention the difference. Without those 2 things, I don't know what the sequence is. I need to know where to start, I need to know what to add every time. And it's trying to be simple in the sense that I'm adding the same thing every time. So we're trying to make things specific and simpler to try and get a handle on all these A's and N's and D's and stuff that we see. Any other thoughts? Is it slowly making sense every day a little bit more? That's what we're aiming for. A little bit. Yeah.
So if an arithmetic sequence is also recursive and explicit,
Yes.
and it says you need the first term, do you need the, but I didn't think you needed the first term for explicit.
Well, in this case, it turns out I do. It's right there. In this kind of sequence, I do. Yeah.
Do you
So
also-
it's not stated separately. It's built into the formula already.
You need both of them to have the first term.
In this case, not in general. There could be some explicit formulas where the first term doesn't appear directly. In arithmetic sequences, yes, you need them for both.
So
There are many other sequences, right? We're trying to avoid them because they're complicated.
Explicit and recursive were subdivisions of arithmetic sequences.
So recursive and explicit are 2 formulas for the exact same thing. Like one is your birth certificate name and one is your nickname. It's both you, but it looks different. And when we say
Arithmetic sequences.
they're both the same thing, different ways to represent the same thing. Like your name and your nickname, they're both representing you, but it's not the same name. The formulas don't look the same,
No, I'm not.
but they're
confused
both
about that.
talking about the
Are
same
they a
thing.
subdivision of arithmetic sequence?
Yes, they're both arithmetic sequences.
Okay, because on the arithmetic sequence, you said you need the first term. And
Yes, you
said
do.
Explicit, you don't always need the first.
Yes, it's right there.
You said this time.
For arithmetic sequences, there are many other kinds of sequences where their explicit formulas won't look like this.
Okay.
The arithmetic sequence type always looks like this, and it always needs the A first term. There's many other types. We're trying to avoid them because they're complicated. And we saw the four base ones that we memorized yesterday, they're not arithmetic sequences. Their formulas look different. So there are many other kinds. In an attempt to try and make things as easy to get a hold of as possible, we're looking at a simple one kind of sequence. But it still has multiple formulas to refer to the same thing. Anything else? So now, I certainly don't want to go through this explanation every time to try and get to the explicit formula. So it's definitely a good idea to memorize the look of the explicit formula. The recursive formula is a direct translation. I don't feel the need to memorize it. But the explicit one, I like to memorize that one for convenience. All right. Now we have three kinds of questions. One is, here's a random formula. Is it an arithmetic sequence or not? That's exercise 2.4 we'll do first. So, our first formula that we might have seen before, I think I got lazy and just copied the same formula. Whoops. Just because it doesn't look, oh, first of all, is this an explicit or a recursive formula? You need to get used to these things, right? Explicit, because only the position is used to calculate the term. And no previous terms are required. Okay, side note. It doesn't look like the one I memorized. That doesn't mean it's not. I could make sure by making a few terms in the sequence and seeing what the jumps are. So the first term is going to be position 1, so 2 times 1, so 3. Next one, 9. I think we've done this one before. That's okay. When the position is 3, I get a 9 here, 2 times 19, yeah, sure. And I can keep going, but I already see that this jump is a 6, this jump is a 10. It's not the same. So it's not an arithmetic sequence. Our goal is to try and keep things as simple as possible, and having the jump the same is important for that purpose. Everyone happy that it's not an arithmetic sequence? No one is looking happy. How can I make you happy? By changing the topic? Soon we will. Probability is going to be a completely different topic, which could be a good or a bad thing. Just as you're getting on top of this, we switch it up.
Can you just go over how you got those numbers again?
Which position do you want?
Just from the first one.
First position is 1. I plug in a 1 for n. Calculator, answer.
So 1 to the power 2 times 2 plus 1. So just use 1 the entire time plus 1. Oh, no lies.
Yes, n is 1.
Plus 1. Yeah.
And then I multiply by 2.
Oh, yeah.
Whoops.
So
Oh,
2 plus 1. Yeah.
I need to play with it. Then position 2. The n is 2 for that one. Plug it in wherever you see an n. Calculator, calculator. 9 comes out. Whether that calculator is your head or an actual calculator, doesn't matter. Well, it matters a little bit. It'd be good to do it in your head. Good practice. Then position is a 3. Calculator, calculator. 19. So the explicit formula is actually much simpler to work with, in that I just need to know what my position is, plug it in where I need to plug it in, calculation comes out. I don't care what other terms are around me, only the position. So I could skip some and go to that position, but I want to see the difference in the jump, so I want to do it in the sequence. And because that jump's not the same, it's not an arithmetic sequence. That's okay. Number 2. A n is 3n minus 1. Now, that does not look like the one I memorized. That doesn't necessarily mean anything. I could make my sequence still an explicit formula and see how the jumps behave. First term, plug in a 1, I get a 2. Second term, 5 he says, and then 8, plugging in a 3, getting an 8, plugging in a 4, getting an 11, plugging in a 5, getting a 14. And then I see, well, the jumps in this case are all the same. So whether the formula looked exactly the way I memorized it or not, this is an arithmetic sequence. Arithmetic sequence. And when I say that, I have to say first term is a 2, and the difference is a 3. So get into the habit when you say something is an arithmetic sequence, it's always followed by what is the first term, what is the difference. That's the full sentence. Because if I tell you, I'm thinking of an arithmetic sequence, you can't make it. You don't know. You need to know those two numbers to copy and make the sequence. If we're happy that that is an arithmetic sequence. I'm going to skip number 3 and make my own number 4 because I want to. I'm going to give you a recursive formula. Let's go with a 7. And then maybe say an minus 1 plus, I don't know. Now, recursive formulas have another benefit in that they are easier to recognize. I could just look at the previous page here, look at my recursive formula, and see this has the exact same look. Different starting point, different number I add, but the look is exactly the same. So I suspect it's an arithmetic sequence, but you still can confirm that by making the first 5 or so of the sequence. So I start with a 7. The instructions are much more direct for the recursive formula. Add 2 to the previous one. So 9, 11, 13, 15. Clearly an arithmetic sequence. Arithmetic sequence with first term 7 and difference 2. Yes.
Did you want that sentence, or do you have this
I
question?
always want that sentence.
Great.
Just get into the habit of when you write down arithmetic sequence, it's followed by everything. Then there's no issue ever. Good habit. It doesn't take that long to write down. So the recursive formula is a little easier to recognize. There's not any tweaking I can do to make it confusing. I'll do another one. Let's go. A1 is, I don't know, you pick a number.
17.
17. let's go an is an minus 2 plus 3. Actually, I need an a2 here as well. Let's go 19. Actually, no, let's go 20. There we go. Recursive formula. Good practice to read these formulas anyway. So a lot of this helps me with the previous chapter. The concepts are still sequences. So they give me the first one. They give me the second one. What is the next third term? I agree it's 20 or 23. It's not 22, no. 20 or 23. What does the instruction say? Look 2 steps back and add 3. N minus 2. Right? That means look 2 steps back. So if I'm in position 3, n minus 2 is position 1, and that's what I use to add 3. So it's this guy, 17. So it's another 20. Now you can right away see this is not an arithmetic sequence. They double, no. But it's good practice to do the rest. Position 4, 2 steps back, 23. Position 5, 2 steps back, 23 again. So that's very much not arithmetic. Just sort of as a side practice, extra practice, reading formulas. Because that very well could have been, or could be, quiz 1, page 1. Question 1. Most pages have an A and a B. Part A will be, here's a formula, make the sequence. Could be this one. We forgot something in this question. The question says, determine the other type of formula if it is an arithmetic sequence. So they've given me in number 2 an explicit formula. I've identified it is an arithmetic sequence. I have to make the other type of formula, which means I have to make the recursive formula, which is first term 2, then go take the previous one and add 3. We forgot to read the question. They've given me 1, I make the other one. If it's not an arithmetic sequence, then it doesn't matter. But if it is, what is the other type of formula? And in number 4, it was an arithmetic sequence as well. So I was given a recursive formula. I need to make the explicit formula, which I've memorized. First term plus n minus 1 times difference. Handy to memorize that one. All right. How do we feel about arithmetic sequences and their formulas? I'm trying to make them as simple as possible. It cannot be simpler than the same jump every time. How do you feel about the recursive formula?
Recursive is just the position value. Explicit.
That's literally the translation of jump 3 every time.
Great. And then explicit, you need the...
I think remembering what the look of it is a good idea, and then you're just filling in the first term and the difference. It's always the n minus 1.
And explicit?
Yeah. So there's a look to it that I memorize. I always memorize a plus n minus 1 times d. And then for a specific example, the a and the d have numbers I can put in. Yes.
Sorry, I just missed where you get the jump 2, jump 3. Is it always the same for...
Arithmetic sequence, the jump is always the same.
And if for that one it's 3 or 2?
No, it depends on the example. Yeah.
But where
Our
in the
first
example
example
are you
was a
finding
3.
it? Like where in the example are you finding?
You look at the sequence. What's the jump? Where's my cursor? Jump is, oops. The jump is 2.
Oh, yeah, sorry, okay.
So that is the 2 right there.
And that was why for 17 to 20 was
And then another sequence, if it's not arithmetic, then something else. This one, jump is 3. So that 3 is also in the recursive formula. Yeah.
So on the quiz, will be asked if it's an arithmetic sequence and then to find.
Quiz specific. Page 1 is not this, right? Page 1 is, here's a formula, use it to make a sequence. And page 2 is going to be this. What is an arithmetic sequence? What are the formulas? You can use an example to help you. You can keep the A and the D, doesn't matter. But you have to say the sentence, arithmetic sequence with first term, blah, difference, whatever, and the 2 formulas. That's page 2. And then we have to get to exercise 2.2 and 2.3, of course. I'm just thinking the quiz. Yeah. Page 2. All right, so how can we use this or practice it in little variations of the same kind of sequence? 2.2.
What, sorry, can you just clarify this? I'm confused about
You're
this
going to get a quiz Tuesday the 21st.
Okay.
The quiz is going to have 5 pages. As we do it, I'm just motivating people that this is important, it's on the quiz. That's all. So chapter 1 was page 1, which has an A and a B. Page 2 is really what we're on now. Because sometimes when people hear it's not on the quiz, they just tune out completely. So I'm trying to help the motivation. How many terms are there in the sequence 1, 5, 9, 13, all the way to 125? If you were to give this to little Timmy, assuming he can do the additions, what is he going to do to try and answer that question?
5, probably. Use 5 numbers up there.
Well, yes. Now you've clarified the question. He's understanding that those dots mean lots of numbers. You have to count how many there are in total. What is he going to do now?
Just keep adding 4.
He's just going to keep adding until he magically hits 125 if he didn't make a mistake. And because there are so many numbers, mistakes are very easy. But surely that cannot be the most efficient way to do it. What kind of sequence is this?
Arithmetic.
It's an arithmetic sequence, which gives me a fighting chance to exploit the formulas and the patterns that I already know. So it's an arithmetic sequence with first term 1 and difference 4. Because I'm adding 4 every time, I could say that. Which means I know the formulas, they're already done, I've memorized them. I know everything there is to know about arithmetic sequences, and I can maybe use that to find the answer more efficiently. Now, the recursive formula is kind of useless for us in any sort of calculation. It's a nice translation, but that's pretty much where it stops at this level. Explicit formula is much more useful, but I had to memorize it. So I'll write that down specific for this sequence, which is a 1 first term plus n minus 1 times the difference. So I don't rethink, why is that an n minus 1? No, I'm going to have to do a whole thing if I want to do that. I just memorize it. Knowing that I can explain it if I really want to, but it's a little time consuming. It's not the point here. So, I know I eventually will get a 125. How can I figure out how many terms there are in this sequence? Sure, but technically the formula already captures that table, right? The table was to get this. So, but it's not wrong, it's just unnecessary. There are positions for all of these terms, right? People forget those positions. They're very useful. And I can rephrase the question. If I want to know how many terms there are, it's the same question as asking what is the position of 125? Because the positions are counting them exactly the way I want. It always starts with 1, 1, 2, 3, 4, 5. So the position underneath the term 125 is going to tell me exactly how many there are. Is everyone happy with that? That's the benefit of positions. They're counting it for me. And the position features in my formula. So that means all I need to do is set the general term name to 125 and find the corresponding value of n. I just have the information a little backwards. Usually, to use a formula, I have to have the position number, position value, and I plug it in to find the term. Now I have the term, 125. I want to find the value of the position that matches it. The formula is still the way to go. So I have 125 as the answer, if you will, to the formula. And I want to know what is the position that would give me that 125. Everyone happy with why we're doing that? It's just the information is just backwards. Now, depending on your algebra skill, you can do this in as few or as many steps as you want. I'll do a lot of steps because it doesn't happen often, so I don't want anyone to be too confused. I'll multiply the 4 in first and only do one thing at a time. The other things stay the same. 4 times n is 4 times n. 4 times 1 is 4. Then I'll put the like terms together. The 1 minus the 4 will give me minus 3. Then I want to get this minus 3 away from the variable, the unknown, so I'll add 3 to get 128 equal to 4n. I don't like my unknown on the right. I'm going to swap everything. This is now a lot of detail. You don't have to do it in this much detail. Then I'll divide both sides by 4 to get n equal to 32. Do any version of that, as long as you get 32. That could be remembering 142, variables and equations, yeah. Or relying on your prerequisite, which I believe is Math 11. So, one way or another, you have seen these things before. 32. And that's it, that's the answer. There are 32 terms. Because the position counts them exactly the way I want. So there's one example where the explicit formula is very handy. And the recursive formula is quite useless. Recursive formula is weird. It's a good first translation of and showing what the pattern is. Then it's put on hold completely. And then at the higher level, it comes back in a big way, but we can't see. So really, explicit formulas are the useful ones to actually use in calculations. Any questions on that one? How do we feel so far? Remembering that it's math and our feelings are quite irrelevant. But you can still pretend they're important. arithmetic sequences will not change. I can have a happy day or a sad day. They are the same. It's very comforting. They're always the same. Not going to change. So, memorizing the explicit formula for an arithmetic sequence, very handy. Let's take it up one more level, because why not? You have to challenge ourselves. If you don't challenge yourself, you don't grow and improve with something equally profound. It's exercise, oops, that was not V3, I apologize. 2.3. And it's all just about how the information is given. It's all still arithmetic sequences. It's just, is the information given in a nice way or a tricky one? So, determine the explicit formula for the arithmetic sequence having 10th term 32 and 23rd term 71. And then use the formula to do whatever. Once I have the formula, I know everything. Essentially, the formula is a name for the arithmetic sequence. It tells me everything. So the information is given in a weird way. I'm not sure what the first terms are, and then it keeps going until the 10th one, which is a 32, and then it continues until it hits the 23rd one, which is 71, and then it probably continues. So because of that inconvenience, I have to think a little bit more carefully how I'm going to approach this. I know it's arithmetic, which means there is a first term and a difference, a jump that's always the same. So let's just remind ourselves what we call those. The first term we'll call A, and the difference we'll call D, because I don't know what they are. And they both feature in the explicit formula, so my goal here really is to find the values of these guys so that I can set up the explicit formula. Now I know the A goes over there, I don't know what it is. And I know the difference is what I'm adding every time. I need to figure them out. So let's work with what we have, which is the 32 and the 71. And let's go from 32 to 71. To do that, I'm going to add the difference a number of times. To get to the 11th term, I'm going to add D. To get to the 12th term, I'm going to add D again. And so on, until I hit 71. How many times did I add D from 32 to 71? Let's suppose I'm not sure. Not sure. I need to be 100% sure. What can I do to help myself be sure? I like a little table. Big advocate of the table. So I want to have one column position, or let's say I'm getting to a position, and then the number of jumps. That's the thing in question. So I'm starting at 32. To get to position 11, I make one jump. Yes? Is everyone understanding what I'm doing? To get to position 12, I've made 2 jumps. To get to position 13, I've made 3 jumps. So if I keep going, to get to position 23, how many jumps have I made? Well, what's the link between the left and the right column? Take 10 away, so 13. So we can sort of make one super jump and say that is 13 jumps of D. Now I know to some of you, you're sitting there, of course it's 13. It's 23 minus 10. Yeah, but it wasn't obvious to everyone. I saw some frowns. I wanted to clarify. I wasn't sure. I had a frown. I needed to be sure. And of course, the more you do this, the easier it does get, like everything. But you can do some stuff on the side if you need to. So, what do we now know? That 32 plus the super jump of 13 Ds will get me to 71. And we are just translating what we've already said into an equation. The equation is not new, it's not strange, it's not magic, it's just a translation of what we've already said. Then I can use that equation to solve for D, subtract 32 on both sides. 13D is, and then you say, nothing about it. You have to say something. Yeah, 39. And then I divide by 13, of course, to get D alone as 3. So now I know the jumps that I'm making is size 3 jumps. And I can go and erase this and this and be a little bit more specific. I'm jumping by 3. Now we've used the 32 to 71 move. So we're kind of done with that. I need to find the first term. Well, I go from the first term to 32 with jumps of 3. How many jumps am I making here? Zoom. How many jumps am I making from the first term to get to 32?
10 jumps.
It's not 10. Which is why I like my table, because I do not want to guess. How do I know it's not 10? How do I know? I'm going to do my table again. Because I like that feeling of confidence in my numbers. So because my first jump is to position 2, I've made 1 jump. That's the thing. To position 3, I've made 2 jumps. To position 10, I therefore have made 9 jumps. But now I'm sure. Some people say, of course it's 9. I don't need a table. That's fine. But be sure. So 9 jumps. And I know the size, it's 3. So that means from A, I've made 9 jumps of D to get to 32. So it's the same kind of thing. I just can't use the 32 to 71 again. I have to use another section of the sequence. Now I know this. This is 3. So A plus 9 times 3 is 27 equals 32. And therefore A is 5. So now I have the 2 aspects of the arithmetic sequence that I need. And I know the sequence completely. So my explicit formula for the sequence, therefore telling me everything I really need to know, is the first term plus n minus 1 times the difference. And if, for example, I want to find, like they're asking for the 100th term, that's not a problem if I have the formula. It's simply putting in 100 for n and calculating it. Once I have the formula, it's a formality. Nothing is a mystery anymore. They were just trying to make it a little bit of a mystery by giving me information that wasn't quite convenient. Plug that into your calculator, you get something. What do you get? 302? Done.
So is it 100 minus, it's 100 minus 1? No.
Always 100 minus 1.
Okay,
I've memorized the
it's not
explicit formula.
position before that.
No,
Okay.
nothing. I memorized it. A plus n minus 1 times d. Always. For an arithmetic sequence. Sure, other sequences have other formulas. Right now we're trying to be specific so that we can feel a little bit better.
Just the other day you said like you watch out for like the tiny subscript, like.
None of those are
plus
tiny.
one or-
Well, no,
okay.
that's not true. I guess technically this guy is tiny.
Okay.
But nothing on the right side is. That's the benefit of, another benefit of explicit formulas. There's no tiny subscripts changing my view and anything. I plug in the position value in whatever they say and I calculate it. So that was only the half of chapter 2, but let me just check if there are problems you could be doing. Problem, you can practice problem 2.2, numbers all the numbers, and problem 2.3, and that's it. 2.2, 2.3.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.